This is a National 4-5 chemistry lesson on rates of reaction, and today's lesson is going to focus on measuring the rate of reaction. So the success criteria are: I will be able to make a fair test for measuring the rate of a reaction. I can set up a downward displacement of water experiment to measure the rate, set up a gas syringe experiment to measure the rate, set up a mass lost experiment to measure the rate. You will be able to plot a graph of a rate experiment and compare different rate graphs to determine which experiment was the fastest. Now, normally whenever you are doing a rate of reaction experiment, you would be expected to write a report. The different sections when writing a scientific report are: you need an aim, you need your apparatus, the chemicals used, and a diagram. You would need to talk about the health and safety. You would need a method. You would need results in a table, write a conclusion, draw a graph, and then evaluate your experiment. Evaluating your experiment means determining whether or not your results are reliable and what you could do to improve your experiment if you were to repeat it. We will be going through some of these points in this lesson. So whenever you measure the rate of reaction, you're measuring how quickly something happens. And you can either measure how quickly some of the products are being made, or you could measure how quickly the reactants are being used up. Either one of these will tell you the rate. And if you wanted to, you could even do both on the same experiment and compare your answers. The most common experiment that we use in class to measure rates of reactions is reacting chalk and acid. The sign of this chemical reaction happening is producing bubbles of a gas, and that gas is carbon dioxide. The fact that carbon dioxide is produced in the reaction can be used to measure the rate of reaction. We can measure the volume of this carbon dioxide gas produced over time, and this is one of two possible ways of measuring the volume of gas. Or we could measure how much mass is lost from the experiment over time. So we can either measure what is being formed or measure what is being lost. And we will look in detail at both of those experiments. So the first one we're going to look at, and the first method, is called downward displacement of water. Now you can see this diagram. On the left-hand side of the diagram, we have our reaction happening. So we have our chalk and our acid together inside a flask that's a cone shape, and so it's called a conical flask. There is a stopper inside that flask, and inside that stopper we have a tube called a delivery tube. Now, any gas being produced by the reaction will move through that tube. And that delivery tube goes into a basin of water. And sitting in that basin of water is a measuring cylinder that has been filled with water and turned upside down. Now, if you do it right and turn the measuring cylinder upside down while it's underwater, all the water will stay in the measuring cylinder. As gas moves from your reaction through the delivery tube under the measuring cylinder, it will start to bubble upwards through the measuring cylinder and go to the top. As the gas goes to the top, water is forced out, and so the measuring cylinder slowly fills with gas. And you can use the numbers on the side of the measuring cylinder to record what volume of gas is being produced and use that to determine the rate. So you set up the apparatus like this diagram. You add the chalk to the acid, put the stopper and delivery tube in, and start a timer. Bubbles of CO2 gas will push the water in the measuring cylinder down and start filling the measuring cylinder with gas. Every 30 seconds, you record the volume of gas in the measuring cylinder, and you put that in a table. You stop your experiment once for 3 measurements or 3 minutes, the volume in the measuring cylinder is no longer changing. That's when you know your reaction has stopped. So that means there's no more bubbles. You always need to make sure your results are reliable, repeat the experiment once or twice in order to check that you get the same results again. So that method with an upside down measuring cylinder is called downward displacement of water. Another way of doing the same thing is, instead of using downward displacement of water, you can collect the gas in a gas syringe. Gas syringes are not usually available in schools, and so it's more common that you would use downward displacement of water. However, in National 5 and 4 exams, they may talk about using a gas syringe instead, which is why we're going to teach it to you. You can see the experimental setup is a bit more simple. You still have your chalk and acid in a conical flask with a stopper and a delivery tube, but that delivery tube just goes directly into a gas syringe. As gas is produced in the flask and moves through the delivery tube, it fills the syringe and pushes the plunger of the syringe outwards. And you can use the marks along the gas syringe to measure and record how much gas has been put into the syringe. So just like before, you set up the apparatus, you add chalk to the acid, put the stopper and start a timer. Bubbles of CO2 gas will push the syringe out, and every 30 seconds you can record the volume of gas in the syringe. You stop recording once the volume in the syringe doesn't change for 3 minutes or 3 consecutive readings. And again, as always, you need to reproduce the experiment to check that your results are reliable. So each experiment should be done 2 or 3 times. Now, if you use either of these methods, you will produce a table of results which will look something like this. So this has got 2 different experiments have been done. And you can see that the relationship is, as the time increases, the volume of gas increases. And you can plot that in a graph. Now, when you're plotting a graph for downward displacement of water or gas syringe, you have your time in seconds across the x-axis at the bottom, and you have your volume of gas up on the y-axis at the side. As gas is being produced and slowly stops being produced, you get this shape where it rises up very quickly at the start and then flattens till it's pretty much horizontal. That's how you know the reaction's over. The reaction stops at the point where the graph is horizontal. The reaction is fastest whenever it is going upwards. So you can see that over time, this graph shows that the rate is very quick at the start and then slows down to 0 at the end, because if it's no longer going up, the reaction is no longer happening. You can also measure the rate of reaction by looking at the mass of gas that is being lost from the experiment. Now, to do this, what you do is you do all of your experiment on a balance so that you can record the mass at the start, and every 30 seconds you can see how much gas has been lost. Now, in this experiment, because you're producing bubbles, you might lose gas. You'll definitely lose gas from the reaction, but maybe some of the acid might bubble as well. In order to let the gas escape but keep all the liquid inside, the top of the flask has some cotton wool in it. That cotton wool allows gas to pass through it, but it will absorb any liquid. And that means that you can say that in your experiment, the only thing that's being lost and the only thing that will change the mass of the experiment is the gas being lost, not any splashes of liquid. So this time, the top of the beaker or flask is some cotton wool. So you set up your apparatus like the diagram. You add chalk to the acid and put cotton wool in the top and start a timer. You record the mass at the start and then record the mass every 30 seconds, and you put that in a table. The carbon dioxide gas will escape through the cotton wool, but as I said, no acid splashes can get through the cotton wool. You will stop recording, and you can say your experiment is finished, when the mass doesn't change for 3 readings or 3 minutes. And as with every experiment, you need to repeat it 1 or 2 times in order to make sure that your results are reliable. With an experiment like this, you will notice that the table for for this, the table for this, you see as the time increases, the mass of the reaction decreases. And that is because carbon dioxide gas is escaping. And the mass of the carbon dioxide is what is being lost from the reaction. Once you've got a table, you would then plot a graph. Now, a graph for an experiment like this looks a bit different than if you were looking at the gas being produced. So when you plot a graph of your experiment, you can see it's different from last time. The mass starts quite high and drops quite quickly and then becomes horizontal. The point at which the graph becomes horizontal is whenever the reaction is finished, because that means that no more mass is being lost. That means that no more carbon dioxide is being produced. When you're plotting a graph like this, remember that the time is always going along the bottom of the graph on the x-axis and the mass will go on the y-axis. Now, we use these experiments to determine whether particular factors affect the rate of a chemical reaction. You can, in your aim, you could investigate the effect of changing concentration of acid on the rate of reaction, or another possibility is to investigate the effect of changing the particle size of chalk on the rate of reaction. If you're investigating concentration of acid, what you do is you do an experiment at different concentrations of acid. So you would do a reaction at maybe 0.5 molar acid, low concentration, 1 molar, medium concentration, 2 molar, high concentration. You do each experiment and then you do repeats of each experiment to check that your results are reliable. You then draw graphs to compare the rates. So this is what your 3 graphs would probably look like. You can see that the bottom graph, the one that's lowest down, that is the least steep, is the lowest concentration of acid. Then the one in the middle is the medium, and the one that is the fastest is the highest concentration. The steeper the graph, the faster the rate. So we know from this that the reaction done at 2 mol per dm cubed of acid is the quickest, and the one at 0.5 is the slowest because it's less steep. The steeper the graph, the faster the rate. So we know from these examples that the fastest reaction happened at 2 molar acid. And from this, we could make a conclusion that as concentration of acid increases, the rate of reaction increases. And that matches what we learnt in the previous lesson. If we were to take the aim of investigating the effect of changing particle size of chalk, what we would need to do is try a few different particle sizes. And the most common are to use powder, and that is a very, very small particle size. Then use small lumps, which is a medium particle size, and large lumps, which is the largest particle size. Again, you do each experiment, but also repeat each experiment 2 or 3 times to check that your results are reliable and reproducible. You again draw graphs to compare the rates. So this time we can see with our graphs that we get 3 graphs. Each one has a different level of steepness. The steepest graph is for the powder, then the next steepest is for the small lumps, and the least steep is the large lumps. The steeper the graph, the faster the rate, just like we had for concentration. And so the fastest reaction was with powder. And as the particle size decreases, the rate of reaction increases. So the title of this slide should be the effect of particle size on rate. I do apologize for that. But the conclusion from these graphs, we can see that the powder is the steepest, it is the fastest, the large lumps are the least steep, and they're the slowest. So we can conclude that as particle size decreases, the rate of reaction increases, which is what we would expect from what we learned in the last lesson. So to summarize, you should now know about how to do a fair test for measuring the rate, making sure that you do it reliably and reproduce your results. You've learned how to set up a downward displacement of water to measure the rate. You have learned that you could use a gas syringe instead to measure the rate. You also looked at instead of collecting the gas, how you could measure the mass lost from an experiment by doing the reaction on a mass balance. You've learned what needs to be put on a graph for a rate experiment, making sure that time goes along the bottom on the x-axis and your measurement, whether that is mass or volume, on the y-axis. And then finally, you saw at comparing rate graphs to determine which experiment was the fastest. Remember, the steeper the graph, so the graph that gets the tallest, the fastest, is the fastest reaction. So that has been measuring rates of reaction, and we'll catch you next time.